All right. Nothing terribly intellectually taxing today. I figure you guys have a test tomorrow and you're all nervous about it or something. It's not a tough class. You'll be fine. And we'll see what we can do with this. So we'll play around some more with the idea of substitutions. There are a couple of things that we want to look at, a few things I want to look at. We want to look at definite integrals. We want to see what happens with those. We want to look at what happens when you have multiple options for your substitutions. I think I'll start with that one. And you also want to look at what happens when the substitutions end up being fairly difficult and how that works. So I'm going to start with just the integral of sine x cos x dx. That's the classic one because there aren't too many examples where there are three possible substitutions. So this one over here, there are three that you can go with. Two are fairly obvious. One requires a little bit of simplification before we can use it. But first thing that you should notice is if we let u be equal to sine of x, then the derivative of sine of x shows up within the integral, and therefore it makes sense to try to use this as a substitution. So du is equal to cosine of x dx. We can substitute for this directly. And so this simply gives us the integral of u du, which is u squared over 2 plus c. And with definite integrals, you have to go back to the original variable. So this is sine squared of x over 2 plus a constant. Okay? Any questions, any issues, any problems with it at all? Okay? All right. So, second example. Let's look at the integral of sine of x cos of x dx. But this time, we'll take u is equal to cosine of x. It's less obvious because its derivative is negative sine x. And so I can substitute for this. It still leaves me a minus sign that I have to contend with. That's not a big deal. But it is clearly slightly less nice than the example on the left. So over here, this is equal to the integral of negative u du, which gives us negative u squared over 2 plus a constant, which gives us negative cos squared x all over 2 plus c. Which is definitely not what we have over there on the left. But there is a third variant. So let's just do this democratically. We integrated 3 times, and then whatever we get 2 of, that's the one that wins, and therefore that one has to be correct. Right? That makes sense, surely. So we look at the integral of sine x cos x dx. And we think about the fact that sine of 2x is equal to 2 sine x cos x. And so what we can do is we can write this as the integral of 1/2 sine of 2x dx. And so a simple u is equal to 2x, du is equal to 2 dx, gives us the integral of 1/2, or better yet 1/4, sine of u du. I can integrate sine pretty easily, right? That one comes out to negative cosine. So this is negative 1/4 cosine of u plus c. And so this is negative 1/4 cosine of 2x plus c. Split vote. Okay, so we've got 3 different possibilities. But there's a trick here. There's a simple trick that I'm using in order to make this look a lot more confusing than it is. There's no reason why this c should be equal to that one. As a matter of fact, it should be a different constant. So let's make this guy c1, let's make this guy c2, let's make this one C3. These are three different constants. And therefore, there's at least a chance of these things being equal to each other. So for example, if we try it, if we let sine squared x over 2 plus c1 be equal to negative cos squared x over 2 plus c2, makes some sense to take this cos squared x, throw it over to the left-hand side. And then what we're going to have on the left is sine squared x plus cos squared x all over 2 plus c1 is equal to c2. So c1 plus a half is equal to c2. That's fine, right? They're both constants. They differ by a constant. That makes perfect sense. Now, if I had something in there that was a function of x, that would be problematic. But I'm pretty confident about the mean value thing. If I ended up with something that was a function of x, my guess would be that I made a mistake on one of them or the other. Right? Because the other possibility is that math is wrong, which is possible, but it's really not the result that you want to end up with. That's not where the smart money is. So you can have multiple people walking through a question. They can have vastly different looking, not just solutions, but answers. And yet they could both still be correct. So if you're ever checking, and this is one of the important things about integration, you can check your work. If we're asking you, find the integral of f of x, and you give us an answer, right? So one of these guys over here, you can double check it. You can take its derivative, and you better end up with the original function. If you don't, then you made a mistake somewhere along the way. Possibly in checking it, but it has happened. Right? So if you and a friend are working together on a question like this, and you end up with different looking solutions, it doesn't mean that you're both wrong. You should both immediately double check your work. You should see what's going on and then figure things out from there. And if you find that you did have two different paths to a correct answer, then you should figure out what it is about the question that indicates this. Is there something about it that kind of gives you a tell that something is going to happen? So for example, if I had to integrate, let's say, sine cubed of x cos of x dx, it makes an awful lot of sense to take u is equal to sine of x, because then du is equal to cos x dx. Again, that substitutes this entire part over here. And so I'm going to get to the integral of u cubed du, which is equal to u to the fourth over 4 plus a constant. So it's sine to the fourth of x over 4 plus a constant. Pretty straightforward stuff. However, if I have to do this on a day where I decide, you know what, I'm going to do things in a contrary manner just for fun, which is not actually a bad idea. It's not a great idea on a test, but while you're doing homework, it's actually a very good way to study. So let's say we have the integral of sine cubed x cos x dx, and you decide, you know what, I want u is equal to cosine x. I've got no guarantee that that will work, but I'm going to give it a shot and I'm going to see what happens. Then du is equal to negative sine x dx. And so it takes out one of the factors of sine x, but not all three. It leaves a couple of them behind. So we're going to end up with sine squared of x times u du with a minus sign out here. And obviously we're mixing up different types of variables, so we don't want to do that. We want to avoid it. We're going to write it this way. Okay? Sine squared, I can always switch into cosine squared. I can write sine squared of x as 1 minus cos squared of x, which for us is equal to 1 minus u squared. So I can write this guy as negative integral of 1 minus u squared times u du. I don't know any rule about integrating a product, so I have to multiply these guys out in order to see what happens. And I get the integral of u cubed minus u du, which gives us u to the 4th over 4 minus u squared over 2 plus, I've already learned my lesson, I'm not going to take just c, I'm going to write it as c prime, c1, c18, whatever you want. It is something to indicate that it's different from the one before it. And so this is cosine to the 4th of x over 4 minus cos squared of x over 2 plus our new constant. Yes? Oh, I skipped a step. I brought it in at the same time. So this guy becomes u squared minus 1, and that's where I get those. Yeah. Sorry, I do this more often than I would like to, but I don't seem to have managed to completely cut it out of the way that I do solutions. It's ingrained by now. Okay, any questions? Yes?
I know you expanded the integrative, but would there be a product with principle?
So that's what we're going to at the end of this section. Once we're done with substitution, we're going to go to integration by parts, which looks at the product rule, but we're going to find out it's complicated. Yeah, it's got some issues, but it's a very powerful method. So we will definitely cover it. Okay, more and more examples. Let's look at the integral from, not from 0 to 1, definitely not, from 1 to e of ln of root x, or better yet, of the square root of ln x over x dx. If it was ln of root x, just take that square root out of the ln as multiplication by half. All right, so we want to substitute for the smallest block that is giving us difficulties. What does that mean in this case? There are a few options. I'm not a big fan of the x in the denominator, but I think having a ln x inside a square root, that's probably the ugliest part. It's not so much the square root, it's having the ln of x inside it. So I would look for this as my first guess at what is the smallest block that's giving me difficulties. Okay, and you want to do a lot of homework for this section because that's what it trains you for. It trains you by the time of the test and of the exam to be able to more confidently figure out what is the likeliest substitution to work. All right? It's not whether you get these right or wrong. As a matter of fact, just get it to the point where it's clear that you can integrate it. That is better than nothing. All right? So over here, we would try u is equal to ln of x, du is equal to 1 over x dx. Immediately, that seems to be rather positive. It's clearing out something that we also didn't like. And so we have the integral of the square root of u du. If it was an indefinite integral, this is sufficient. Okay? However, there are bounds to our integration. What I strongly recommend, what we will always recommend, is take these bounds and change them with the substitution. Okay? If I take x is equal to 1 and u is equal to ln of x, then u is equal to ln of 1, which is 0. So this becomes a 0 over here. When I have x is equal to e, that means u is equal to ln of e, which is 1. So that becomes this 1 over here. Okay? If the bounds end up reversed, don't worry about it. Just write it as is. The lower bound becomes the new lower bound. The upper bound becomes the new upper bound. Strictly speaking, you don't have to do this. if you really wanted to, you can leave out the changing of the bounds. I don't recommend it, because the way that most people do it is they'll keep writing this as the integral from 1 to e. But u is not going from 1 to e. So that would be incorrect, and you lose a mark automatically. And that's supposing that at the end, you still remember to do everything correctly and go back to the original variable. Because if you forget to do that, then you lose another mark. And when the question's out of 4, you ain't got a lot left. Right? So it's a high-risk kind of a decision, on top of which, over here, the next step, well, just because we haven't done this too many times, let's write square root in terms of its exponent, so u to the 1/2. And so this is going to be u to the 3/2 times, or divided by 3/2. And we simply evaluate this from 0 to 1. Because we've got these new bounds. And they indicate what the variable is going to do. So we just plug them in. If we had not changed the bounds of integration, then we get over here, and it's from something to something else, and we don't know what those are. So we have to switch back to x, which causes a very lovely spot where you can make an arithmetical mistake and drop marks that you didn't need to drop in the first place. And then you figure out the answer, and it's going to be the same value because it's the same integral. So why take that extra risk? There are about 3 different places where you can screw up by not changing the bounds of integration. So change them. Bring it to whatever this guy says over here. Now we've got 1 over 3/2 minus 0 over 3/2, which is equal to 2/3. And you're done. Don't get fancy with it. If your teachers in high school taught you substitution without changing the bounds of integration, frankly, they did you a disservice. Okay? Yeah.
Why does definite integrand does not have a constant?
Does not have a? Oh, the plus c? Because it doesn't matter over here. Right? Well, what we saw with the fundamental theorem of calculus is that over here you would end up with some function big F of x plus c, and we're evaluating it from a to b. So this is equal to big F at b plus c minus big F at a plus c, and it's the same c. They'll cancel out. So there's no need to put it. Very convenient. Really nice to have. Okay, any questions so far? All right, let's keep going. Let me make sure I got this one correct. Let's take the integral from -5 to 2 of x times the square root of x squared plus 96. Don't be scared about the 96 over there. It's there to make things easier. Okay? I know it doesn't look like it originally, but it will end up being nicer. Smallest block that's giving us difficulties has got to be the thing inside the square root. Okay? Right away. The x is not a problem. The square root by itself, like we saw over there on the top in the middle, square root is not a problem. It's the stuff inside the square root that's giving us difficulties here. So u is equal to x squared plus 96. Du is equal to 2x dx. And so we have the integral of 1/2 square root of u du. Simple enough. Now, the bounds. The bounds of integration. When x is equal to -5, it implies that u is equal to 25 plus 96 is 121. which is 11 squared. So it's going to make the arithmetic nice, because we can take the square root easily. Okay? So this guy is 121. When x is equal to 2, for some reason it doesn't bother me what order I do these in. If you prefer to write them top bound over lower bound, then do it that way, right? That way you always substitute them into the right place. This guy goes to 100. And we can keep going. I mean, we know the integral of the square root of u. The rest is going to be straightforward, right? This is going to be a half times u to the 3 halves over 3 halves, evaluated from 121 to 100, which is equal to, bring that 2 inside, and we end up with 1,000 minus 1331 all over 3, whatever that's equal to. Okay. As it is, perfectly fine, no major issues. But when x is equal to 0, we're definitely inside this bound, right? Inside this interval bound. 0 is definitely between -5 and +2. The value for u when x is equal to 0 is u is equal to 96. 96 doesn't show up over here. It's gone. So what happened? How did we lose a part of our interval? As a matter of fact, if we look at it carefully, what we find out is that everything from -2 to +2 went away. All of that gives us values of u that are outside of this area over here. As a matter of fact, we can go even further. If we had the integral from -2 to 2 of x root x squared plus 96 dx, and we use the exact same substitution, then we would end up with the integral from 100 to 100 of 1/2 root u du. What's the area under that graph? 0, yeah, absolutely. Goes away. Here's the really nice thing. That's not a problem. That's fine. Look at what happens. For this to take place, this function over here, remember we discussed symmetry. What's the symmetry of this function? Odd function, absolutely. Which means that its integral from -2 to 2 is equal to 0. Yeah, it's got to cancel out. Right? What this substitution does, and it's not just the value for u, it's u and du together, the way that they work together. What it does is it sort of sucks up the idea that this is an odd function, and it folds it up against itself so that the positive and the negative areas, they just cancel out, and then we don't even need to look at them anymore. Right? The mathematics behind this is really intelligent. It will take care of pretty much anything that we try to do. All you need to do for your substitution is just throw in what it is that's going to happen for the top bound, what it is that happens for the bottom bound, and you're done. As long as your function is properly defined throughout that interval, as long as it's continuous, you're going to be okay. Don't substitute anything where you're going over a discontinuity. That is an issue, but it's an issue that we will look at in calculus too. So you don't really need to worry about it yet. Yeah.
But we want to find the total area and not consider negative area.
Sorry, that?
Like we are considering the area to be negative when it's under the graph, right? What if we
Yeah.
want to consider just the total area?
Okay, if you wanted to look at total area, then you would have this under absolute values. As soon as you have absolute values, you split it up into cases. Here's what happens with the positives, here's what happens with the negatives, and I do each one separately. Okay, and eventually it works out to whatever it is that you wanted. Whenever you're looking for total area, You're just throwing absolute values over the whole thing. And then, as we do throughout when we have absolute values, we take cases and we see what happens. Okay? Yeah?
So I'm really confused about where the x went in that and where the half came from.
So what happened is over here for du, I had x dx. So this x dx, I can substitute them out. And I'll be left with, on the other side, du. And this 2 needs to come over here as well. So it'll come in as a half. So I've got a couple of options. I can either write dx is equal to 1 over 2x du, substitute that in with that middle step, cancel things out best I can, and go on from there, which is, like I said, it's perfectly fine. You want to be able to get past it eventually because it'll just make you significantly faster. But there's nothing wrong with writing down that step. The other option is to look for the best substitution you can. And I've been doing this for a long time. So I'm very comfortable with it. Right? And so I substitute for x dx, leaves me with a half du to put over here, and that gives me my answer. Okay? Do both as many times as you can. Right? Start with taking that middle step a lot, and then bit by bit, start removing it from your calculations. Okay? Any more questions? All right. Let's do. Yeah, this one's good. Okay. Integral of t plus 2 times root t minus 5 dt. Okay, again, smallest block that's giving us difficulties. I'm not a big fan of the t plus 2. I'm not a big fan of having to multiply it by the square root. But in the end, the only thing that is problematic, the only thing that's causing me real difficulties, is the t minus 5 over here. So I would substitute for that. Okay, u is equal to t minus 5. du is equal to dt. That's easy enough. I don't need to do anything with that. And so that gives me the integral of t plus 2 over here. Okay, substituting for the t, that's not necessarily something that's easy to do in your head. So on occasion, I will solve for the one variable in terms of the other over here. Okay, it's a compromise between having that middle step where I've got all of the workings written out and being able to do the whole thing in one shot. So t is equal to u plus 5. Now I can just write this directly as u plus 5 plus 2 times the square root of u du. This is now the integral of u plus 7 times the square root of u du. Again, we don't have the product tool quite yet. We will sometime soon. So this is the integral of u to the 3/2 plus 7u to the 1/2 du. U to the 5/2 over 5/2 plus 7u to the 3/2 over 3/2 plus a constant. We should simplify that a little bit. Besides, we need to take an extra step to go back to our original variable. So 2 times t minus 5 to the 5/2 all over 5 plus 14 times t minus 5 to the 3/2 over 3 plus a constant. Okay. Very mechanical stuff. The great difficulty when we're dealing with integration is figuring out what the correct method is going to be. Once you have figured out the method and its details, so generally what the correct substitution is going to be, then the rest is just being willing to sit down and trust your arithmetic and bash your way through it until you get to the end. Right? Nothing too dramatic throughout. All right. One last little detail. This one's completely optional, but it's something that I've certainly noticed over the years, and I like it. I generally opt for using this whenever I see it. Let's say we had, let's go with a definite integral from 0 to 1, x cubed over root 1 plus x squared dx. Definitely not pretty, definitely not nice or friendly, but smallest block is pretty straightforward to find out. It's going to be a 1 plus x squared. And almost every time, I would use u is equal to 1 plus x squared. My one exception, and again, completely optional, this is something that I'm aware of as a time saver, but you don't ever have to use it. When you have a square root in the denominator, then and only then, it tends to be a good idea to keep that square root, that exponent, with what it is that you're substituting. Okay, why? Because then when I take du, I'm going to have 1 over 2 times the square root of 1 plus x squared times 2x dx, and that gets rid of that square root in the denominator. Right? It's a cute idea. It's very clever. If you see it, great. If you don't, it's going to cost you maybe 30 seconds. It's not a big deal. But it's neat when you can do it. Right? It really simplifies the situation very quickly, because in our case, we're down to an integral, first of all, from the square root of 1 to the square root of 2. We're substituting for this whole thing, right? So x over root 1 plus x squared dx. It leaves us with just an x squared at the top. So x squared, well, over here I've got u squared is equal to 1 plus x squared. So x squared is equal to u squared minus 1. So this is u squared minus 1 du. No square roots. I'm just integrating a polynomial. And when you're dealing with a definite integral, this is really nice. It's even nicer than before, because you can just get right to the answer without having to ever substitute back. Yeah? This guy's x cubed. I'm going to need one of those x's over here, and then the x squared that remains becomes u squared. You're going to learn very, very quickly that you've got to be careful with the what we refer to as the parity of the degree, whether it's even or odd. So if you're trying to integrate, this is not a part of the of that discussion. If you were trying to integrate this, then that substitution over there will not work. U is equal to 1 plus x squared will not work. You will need a completely different type of substitution in order to figure this one out. Okay, so I'm going to leave it in your hands. See if you can figure it out. If you can't, that's fine. We'll come back to it in Calculus 2. Okay, so within a couple of months, either me or Bernardo Sousa, one of us will cover this question. All right? Now, this one over here, just for completion's sake, u cubed over 3 minus u from 1 to root 2. So this is 2/3 root 2 minus root 2 minus 1/3 minus 1, which is equal to 2/3 minus, this is 2/3 minus negative root 2 over 3. Which is about 0.2. Okay. So that about does it for substitution. Any questions so far? We're good with this? Practice. Lots and lots and lots of practice. Then we get to the fun stuff. Integration by parts. You guys get to be the guinea pigs. This is the first time we've taught integration by parts in Calculus 1. Actually, no, sorry. No, we had done this before years and years and years ago in the other calculus, in the one for ECEs. But we certainly haven't done this in quite some time. Integration by parts, the idea is to find a way to reverse the product rule. We want to go back to that one and find out what its reverse would be. Well, the easy answer is that the integral of f prime g plus f g prime dx is equal to fg. Easy, no problem, very straightforward thing. Except, when are you ever going to bump against this in the middle of the night? There's no way that you're going to be given an integral to do that has something like this in it, and you'll go, oh, well, obviously, it's f prime g plus g prime f. Okay? There's no way that I would see it. There's no way that someone who's actually careful when they do math would see it. It doesn't happen in everyday circumstances. It doesn't show up. And most of the time, these two things are going to be sufficiently different looking that what we're going to do is we're going to break apart the integral into two separate integrals, work on each one individually, and completely miss any possible relations. But if we take this one and isolate it, find that integral relative to the rest, that ends up being something that's not just a little bit useful. It's the only method of integration that we learn in first year that is not based on substitutions. All of the rest that we're going to do, first month of Calc 2, you're going to see it's just types of substitutions. We're going to substitute into trigonometry. We're going to substitute away from trigonometry. We're going to substitute in order to solve rational functions divided by other rational functions. We're going to do all of this stuff. But this one is not based on substitutions. And so I can write the integral of f prime g dx is equal to f times g minus the integral of f g prime dx. This guy over here has a plus a constant attached to it. So let's take this guy and just sort of absorb it in. I just change the constant. All right, that's completely valid. So we don't need to write down a plus c just yet. This shows up all the time. Right, the number of applications is a little bit disturbing. So let's just jump to it directly. Do a few of these and see what happens. By law, we are required to do this one as our first example. There's nothing else we're allowed to. If you're feeling fancy enough, you can do x sine of x. Right? Cosine is a little edgy. So we take this thing over here. And if you try to substitute, there's nothing to substitute for. You can try u is equal to x or u is equal to e to the x. Neither one gets you anywhere. And do try it. Right? Do actually take a bit of time where when you're taking a break from studying for tomorrow's test, take a couple of minutes and see if you can solve this one using substitution. And you find out that the answer is no. It might look good for a bit, but then it ends up just crashing against the rocks. So we want something else to do with this. Well, what you can see over there is that when you're looking at f and g, the one that was regular becomes its derivative. The one that was a derivative goes back to the original function. So you're integrating it. If I either take the derivative or integrate e to the x, nothing really happens. On the other hand, with x itself, if I integrate it, it gets worse. But if I take its derivative, well, that's just a constant. That sounds like a nice thing for us to have. So we can try that. Right? And there are various ways of doing this. I prefer using f prime g, g prime f, going through that way. A lot of engineering schools tend to go with so if we write this as the integral of u dv, so if v is its own function, then dv is going to be v prime times dx. So we're using dv for f prime dx over there on the top right. Then this is equal to u times v minus the integral of v du. I'm not a fan of this one. I prefer to see the dx's. I prefer to see this thing handled, carefully. But it's up to you guys. And certainly you will see this in enough books in the future that I really should mention it. So my preferred way of doing this, I will look at f and I will look at g prime. Okay? I want to take the derivative of x. I want to integrate e to the x. It doesn't matter which one you label f, which one you label g. Just make sure you put the derivative sign in the right spot. That's the only thing that matters. Okay, so that's f and g prime. So the derivative of f is equal to 1. The integral of g prime is g, is e to the x. All you need is a single antiderivative. You do not need the plus c at this point. Okay, do keep that in mind, because otherwise you end up with a bunch of extra terms, and sometimes they're actually really difficult to deal with. So all you need is a single antiderivative. Might as well make it a nice one. Right? Take c is equal to 0. If you really wanted to, and you practiced it ahead of time, feel free to, on the test, throw in the occasional e to the x plus 3 and just see what that does to the TAs and to your mark. Should be fascinating, but it's entirely your call. Another reason why I like this, there's no u showing up over there. It doesn't look like a substitution. I've seen people mess up when they use udv, and all of a sudden they've decided that they're doing a substitution, and they're not. And bad stuff happens. So over here, the integral of this product is equal to these guys minus the integral of this product. Okay, you can come up with a nice pattern to write it so that it always looks like a Z or something so that you remember it, whatever. Come up with your own method. For me, I'm comfortable enough that I know what's what. So that could be because I've been doing this for a while. I don't know. It might be that some of you will need some sort of mnemonic, which is perfectly acceptable. One way or another, we end up with x e to the x minus the integral of e to the x. That one we can do. Once you've gotten rid of your very last integral, the plus c better show up. Technically, because of the minus sign here, this should be minus c. If you want to be careful, you can play around with it that way. We don't tend to worry about it too much in this course. We kind of throw in a plus c at the end. As long as it's only being multiplied by a constant, it's not going to make a difference. It will still be a constant. Okay. So if we had tried switching these guys around, switching their roles, and having f be equal to e to the x and g prime is equal to x, what we would have ended up with is over here the integral of x squared over 2 times e to the x. Simple rule is, if you try one variant and the result is more complicated than what you started with, then try the other one. Right? Integration by parts should not make things worse. Right? It is incredibly rare for that to actually be the correct path. Although next class we will see something really fascinating that we'll be able to do with a variant of this. Meanwhile, just one more example before we head out. The integral of ln x dx. Up until now, we've not been able to do this. And when we look at it, this is not a primary candidate for integration by parts because it's only got one part. Parts is plural. So that doesn't make it terribly easy. However, I can multiply this guy by 1. And why not? Now, I definitely don't want to take the derivative of this 1, because that's just equal to 0. And that's going to get me right back to where I started, and everything's going to cancel out. But I can take ln of x, and I can take its derivative. And that makes things really nice, because the logarithm disappears. I can take this 1, and I can integrate it. I might not be happy about it, but this gets cleaned up a lot more than this one gets messed up. So overall, I should be moving towards something which is nicer. So f prime is equal to 1 over x, g is equal to x, and this is equal to x ln of x minus the integral of 1 over x times x dx. These guys will probably cancel out. And so that gives me x ln x minus x plus a constant. And all of a sudden, we can integrate ln of x. We can integrate arcsine, arccos, arctangent, all the rest of those. Okay, so we will play with that next class. We'll figure out a few other very interesting things that we can do here. But just like with substitution, probably even more importantly than substitution, practice. The ability to figure out which one is the function that we're integrating, which one is the function that we are differentiating. That's the thing that saves you half the time on the test. So make sure that you are comfortable with it. All right, see you on Wednesday.